Let's see if I can speak loud enough for people outside to also hear. Anyhow, thanks for the introduction. Very happy to be here to talk about foundation models as real-world simulators. So when I look at the past 10 years in machine learning, I think the most exciting advances are in 2016, where AlphaGo outperformed human Go players, and more recently, large language models and large video generation models are able to generate highly realistic language and videos. And if we were to step back a little bit, try to understand the technologies that empower these advances, we would see that technologies that empowered AlphaGo is actually research going on in this community known as decision making. So in decision making, the goal is to have computers automatically decide on actions to execute in the real world. And as these actions are executed, the real world gives some feedback and what happens next. And we want to utilize these additional information to train an agent to know how to act in the world and how to act better according to the feedback. And we saw that this worked pretty well when we have a really good simulator, such as the example of Go, and we have achieved that in 2016. But the progress in decision making has been slow in terms of having more real world impact beyond Go. And what happened recently is that we saw these large internet scale video and language datasets being used to train these video and language foundation models. So then my question, or the focus of this talk is, can we utilize these internet scale datasets to essentially learn simulators of the real world so that this can bring us back to the initial decision-making setting that we wanted, which is to train agents in a real world-like simulator so that it can learn how to solve real-world tasks beyond just the game of Go. And before I go into the details of how to learn a simulator, let's first understand how could decision-making enable agents to perform better than humans. And if we were to look at when decision-making has worked, let's take AlphaGo as an example. And what happens is that these agents usually have some ways to imagine into the future, right, through these simulated rollouts. And as a result, the agent actually knows more about what happens in the future, like, for example, the outcome of a particular Go game. And then with this additional information, the agent kind of comes back in time and optimizes the current decision. And because the agent knows more about the future than humans, that's how they outperform us. And for this to work, there are actually two things that are very important. First, we need a perfect simulator. The simulator that the agent uses to imagine into the future has to follow the same rules, right, when the agent plays with humans. And on top of that, we need good decision-making algorithms so that we can search and plan in simulation to find the best action. And because the simulator is perfect, then the action found from simulation transfers directly to the real world. This is the setting of AlphaGo. But then once we go beyond these game settings, it's actually really difficult to expect that we have a perfect simulator. These are the simulators that people often use in robotics, which is quite different from what real robot looks like in practice. So as a result, when we develop these algorithms in simulation, the best actions found in these simulated settings rarely transfers to the real world. And of course, we can try to run real robots in real time and try to learn policies by running real robots, but it's very expensive and not very safe. Then the intriguing question is, what if we can learn a realistic simulator? And I'm just going to use the world model as a loose definition for a learned simulator. I will show you what that means later. But you can imagine that in this setting, once we have a realistic simulator, then we can develop these algorithms in simulation. And because the simulator is very realistic, then the actions found in simulation transfers. So given this motivation, I will talk about a series of work, starting with how we can learn world models or learn simulators from internet scale language and video datasets. And next, I will talk about, after we've learned the simulator, how can we combine the simulator with decision-making algorithms such as reinforcement learning and planning to solve real robot tasks. And lastly, I will talk about various challenges and next steps that I think are important in terms of learning real-world simulators using foundation models. So let's begin with learning world models from internet scale datasets. So this first project was really kind of inspired by this observation that we made from language models, that one reason that, in my opinion, language model works so well is because text is actually a unique representation of information. What do I mean by that? Well, different types of information, right? Wikipedia articles or math equations or code can all be represented as text. So it's a very general type of representation or data format. And not just text is a unified representation, but text generation is actually a unified task interface. For example, these different types of tasks considered by the NLP community, such as sentence completion, translation tasks, and also dialogue bots, right? These tasks used to be considered separate tasks, but now they're all casted into a natural language generation task. And as a result, we have a unified representation of information and a unified task interface. We can just gather together the internet scale data and pour these data into the single model using a single training objective. So this has worked great for large language models, but large language models don't really have a visual component, right? And when we talk about learning simulators, there has to be a visual component. And then the bold assumption that we wanted to make is that this actually is true for videos as well, in the sense that video is also a unified representation of information, and that video generation is a unified task interface. So let me show you some examples. For example, if we have some videos of human cooking in the kitchen, and if we condition this video generation model on the initial frame and also on the language actions such as cut peppers, and we train the model to generate this video that corresponds to the execution of cutting peppers, then in some sense the model has learned the notion of cutting peppers. And similarly, to the same model, once we change the dataset into giving it some initial frame of some robots and some low-level control actions like delta x, delta y, how much to move the robot endpoint, and we try to generate the next frame. And in this case, the model has learned somehow of a real-world physics in a sense. And again, we can actually feed the simulated data as well, right? We will have a lot of simulated robotics data sets. We can condition on the frame and some control to try to predict the next frame, and then the model has learned simulated dynamics. And when we have these panorama scans or 3D data sets, for example, we can also introduce actions by language such as turning towards a certain direction. We can generate a video that corresponds to that motion, and in some sense, the model has learned what does it mean to turn 90 degrees to the right. And even when we don't have videos, when we only have images, right, we can still try to generate the image from the natural language input. And in this case, the model has learned notions of what a free speech should look like. So this is like just to show you some examples of why video generation is a unified task or unified interface, right? We can merge a lot of different data sets of humans, of robots, or simulated data, of navigation data, manipulation data, all into one model, right? So I want to go into a bit of a detail of how exactly we implemented this model. So I'll have to go into a little bit of background in the model that we use, which is a diffusion model. So diffusion model was initially developed for images, where when we have some clean image, we can corrupt the signal in this image by repeatedly adding Gaussian noise until we have a fully random image. And what we're going to do during training is we're going to learn this reverse schedule epsilon theta by minimizing the mean squared error between the noise that we added to the image and the reverse schedule we're trying to learn. This is our training objective. And during inference, we can start from a noisy image, and by repeatedly subtracting this learned noise schedule epsilon theta, we can generate a new image. And we can further condition this noise schedule on some control input, some language such as I want to generate an image of a robot, or I want to generate an image of a human. So this is diffusion model for images. What about world models, right? And in world modeling, oftentimes the language is usually specifying some activity, for example, happening in the foreground. Wiping table have this robot. But then the background usually needs to stay consistent. So to ensure that, we replicate the first frame across time and pass this replicated future frames into the video diffusion model to ensure the temporal consistency. And next, we're just going to condition on, in addition to conditioning on the first image, we're also going to condition on some language instruction, such as wiping table, to generate the visual execution, these video frames that corresponds to the motion of wiping table. And lastly, we can also use these temporal super resolution to generate coarse frames into the future first, and then condition on these coarse frames to fill in the gaps, right, to generate more detailed videos. So this actually allows us to generate videos of arbitrary horizons by just either inserting these intermediate frames or condition on the last frame of the previous generation. With a new language instruction, we can simulate that again. I will show you an example later of that happens. And so that's on the modeling side. And on the data side, we really went out of our way to try to gather together as much video data as possible. So you can see some robot data here, real robot data, simulated robot data, human activities such as Evo4D, and these panorama data sets, and also internet scale text image data sets such as Lion. So I want to show you exactly, we've been talking about this world model or real world simulator for so long. I want to show you what this looks like. So in this setting, we actually have diverse scenes to choose from. And really, if the server is running, you can really upload an image of your own and as the start initial frame. Remember, like the model has to take an initial frame. So in this case, we're going to pass the initial frame, which is a first person view, person standing in the kitchen and looking down at a cutting board. And then we can actually choose from these diverse language instructions. And for example, we can choose language such as wash hands, and we see that the person actually went on to wash their hands. And a simulator being a simulator, it has to support repeated interactions. So in this case, after the first action, we can give the simulator a next action such as shut off water. So the simulator has to start from the previous observation of the last interaction to generate this new interaction such as shut off water. And in addition to supporting repeated interactions, a simulator should also support diverse actions such as pick up the ball, cut carrots, or dry hands, all from the same initial frame. And not just that we can generate these diverse manipulation instructions, but we can also try these navigation instructions starting from the same initial frame. We can ask a person to turn left. All of these videos are generated, like they don't exist on the internet. And we see that the person actually turned away from the kitchen and it seems like a dining room showed up. And when we ask the person to turn right, a wall shows up, right? So this is really to show diverse interactions like manipulation and navigation can all be casted into video generation. And not only we can do this for humans, but also we can do this for robots. We can ask the robots to put sponge in a drawer and to take the sponge out and so on and so forth. So, and I actually like this example the most. In this example, we have a napkin sitting on the table, and we can give the instruction of uncover some objects. And you see like a human hand actually uncovers the toothpaste. And furthermore, we can have a human hand interact with the toothpaste, like pick it up, or slide it to particular directions. And we can really kind of use language to structure the output space of this video generation model so that we can see a pen and have a person pinch the pen. You see the distance between the two fingers is really fitting the pen. And so the interaction is really diverse. You can really any natural language instruction that's natural given this setting, you can really kind of try to simulate it. And there are many more examples. You can check it out on the Unison website, like uncover a plate and put an apple on the plate, or interact with a plate in various ways and have different objects and so on. And you can, even put a cup next to the bottle. So so this is some examples of what this real world simulator looks like. And so to recap, the real takeaway from this first part of the talk is that when we have a unified representation of information, such as videos, and a unified task interface, such as video generation, we can really merge very diverse data, and as a result, get these generalizations of new interactions as simulators. Oh, okay. Okay, I'll just try to speak louder. Okay, so that's the first part of the talk. Okay, that's the first part of the talk, and let's look at how once we have this realistic real-world simulator, how are some concrete ways that we can use this simulator to actually train agents? So one decision-making algorithm that has been popularized so much is reinforcement learning, right? So reinforcement learning holds this promise that once we have a simulator, we can just put the policy inside of the simulator. The policy is going to try to execute some low-level actions, delta x, delta y, observe the outcome of the action, such as some reward and next observation, and it can just optimize itself without human intervention. So this works really well when we have simulated evaluations. But once we try to develop a reinforcement learning algorithm training simulation in the real world, we actually run into this trouble known as sim-to-real transfer issue. And even in this very simple task, right? So the task is to rearrange the blocks on the table according to the language instruction. And even in this very simple manipulation task, we see that the simulator and the real world looks very different. So how does the simulated rollouts from Unison look like? So all of these rollouts on the right are generated by rolling out a policy repeatedly, right? Because every time we only predict one frame condition on this delta x, delta y, but then this is rolling out many steps of the policy. And we see that this rollout of the policy actually looks quite realistic in terms of what a real robot movement might look like. And to just show you some examples, we compare it to just directly running behavioral cloning using the same data set. And we see that because the data set is mixed, it has expert data and also non-expert data. As a result, we actually get somewhat of a low success accuracy. But then once we do some RL on top of it, the success rate actually dramatically increases. So then coming back to this diagram, then you can see that on the right, this is actually a zero-shot transfer of the policy directly on the real robot to perform its task of pushing the red star towards the blue cube. And then the policy is only trained in simulator, trained only in Unison. So then like the intriguing thought is that maybe the solution to the sim to real transfer is indeed to have a learned simulator that is pretty much real. So that we talked about some very simple tasks, right? So if you look at this task, right, place your hand above the blue cube or move red star towards the blue cube. It's like very simple, relatively short horizon. We just need to figure out what the low-level controls are. But once we want to do some long horizon tasks, right? So for example, we want the robots to put all of the fruits into the top drawer. So this is a long horizon task that is very difficult to directly train RL policies to perform. So what we can do is that, remember, Unison also takes language as input. So what if we just try to generate a video of putting the fruits into the top drawer, conditioned on the first frame and this language instruction. So this video is generated by Unison. You see that the model actually, the robot opens the first drawer and it puts the fruits in the drawer. But this video doesn't mean that the robot has executed anything, right? So we only have a video. To actually turn this video into real robot executions, we train a separate inverse dynamics model. So an inverse dynamics essentially just takes two images and takes the delta of that two images and try to predict the action that caused the change between the two frames. But remember, like the difference between the two frames is relatively low rank, and it's really just capturing the movement of the robot arm. So this is actually a much simpler task. And on the right, you can see the real robot execution when we use the actions, low-level controls recovered from the generated video to control the robots to perform this long horizon task of putting the fruits in the drawer. So this feels like magic, right? We can generate something and then just directly execute it on the real world, in the real world. And so I guess one thing I wanted to point out is that to generate this video is actually non-trivial, because you see that this video is also pretty long horizon. There are multiple steps involved, right? So how can we make sure that we generate the right, sub-steps every single time? So to go into a bit of a detail of how we actually generated that long horizon video, we started from this initial image and language instruction. So we first asked the language model to break down the task, right? So what should be the first step if we want to put the fruits in the top drawer? And language model tells us, okay, maybe open the top drawer, but it's a stochastic model, so there might be multiple samples. Another action says place banana in top drawer, but the top drawer is not open, so the second action is wrong. But then the reason that the second action is wrong is because the top drawer is not open. So there's some kind of reasoning that has to happen in the visual space. So directly using language to know that place banana in the top drawer, the second action is not good, is not trivial. So instead what we do is that we use Unison to simulate the visual execution of this language instruction. And we see that the action 1, which is to open top drawer, actually correctly simulates this interaction, whereas the other action, put the banana in the top drawer, it just doesn't complete the task, right? Because the top drawer is not open. And furthermore, we kind of need, we want to automate all of this, right? So we wanted another visual language model to be able to tell us which execution or which simulation actually is correct or making progress in the task. So this is when we fine-tune a visual language model as a reward model to help us to distinguish which execution to actually proceed. And now remember, we're only one step towards making this task, right? So we conditioned on the last generated frame of opening the top drawer, and then we ask the visual language model again, what should I do now? What should be the next step if the goal is to put all of the fruits in the top drawer? So then we can sample from the visual language model, use Unison to visualize the execution, and use reward model to select the good branch. And until that, we have the full branch that completes the task. We can use this inverse dynamics model that we talked about to translate this video into robot controls and execute the robot controls on the real robot. So maybe here you can recall that we talked about this AlphaGo setting where we have a simulator that's very realistic, and we can do these broad searches and planning all in simulation, in imagination, right? So to try out different actions to see what happens. And we can do the same now with robotics tasks when we have this realistic simulator. So I want to dive into a bit of a detail as to why we want to do planning with Unison, right? What are some other alternatives? So if we think about robotics tasks, often the times the goal is to derive some low-level control actions from A1 to A7, conditioned on some high-level inputs such as the task, make a line, and some initial image frame. So of course we can try to just learn a policy, right? Using behavioral cloning to do this in one step. But then because this task is very difficult, mapping from something very high level to something very low level, so as a result, we actually need a lot of data. And for this particular task, we can see that behavioral cloning or imitation learning works quite poorly and rarely completes the task. So what are some alternatives, right? So this is also our work, Unify, which what Unify does is it predicts these intermediate frames according to the language instruction, which is make a line. And now, conditioned on these intermediate frames, we can use the inverse dynamics model to recover the low-level actions. And we see that the completion rate maybe increased a little bit, but it's still quite low. And so what was this tree search algorithm that I just showed you doing is that it essentially introduced another layer of abstraction, which is to use language to specify what the high-level tasks are. And we see that the completion rate further increases. So to give you more intuition as to why this hierarchy makes sense, there are a few benefits to having this hierarchy. The first benefit is that we actually have internet-scale supervision for the first two levels of mapping. For example, going from language plus image to language, we actually have internet-scale trained vision language models. And from language to video, we also have internet-scale text video data. So we pretty much get these top two levels of mapping from diverse data sets. And the very bottom part, right, to just like recover the action condition on 2 frames is made much easier. So we broke down this complex task into simpler components while using internet-scale data sets to assist with the top levels. And another benefit is that we can actually use language to search quite broadly into the future, right? Because these low-level control actions might be executing at 100 hertz. And it's really difficult to tell whether, moving like this tiny amount is, having any effect of the long horizon goal of reaching that door, for example. But language actually allows us to search and plan much more efficiently into the future. And lastly, we can do actually search and planning and verification during each of these levels of mapping. And some people often ask me, okay, how does Unisim work when we have these long horizon tasks? So I wanted to show you some example when we just repeatedly try to have different interactions. For example, like the first one is to put the pen on the top. The second step is to close the bottom drawer. Like each of the new simulation is conditioned on the last frame of the previous simulation. And then, we're just doing this repeated rollouts, and you see that the model actually doesn't get worse as time goes on. It just continues to behave the way we expect it to behave. We're already at step 6, and maybe step 7, put the key in the top drawer, and step 8 to close the top drawer. And eventually I just got tired, so I stopped generating. But the point is that it can really generate long horizon videos just by conditioning on the previous generation. And in addition to long horizon planning, we can also actually conduct this multitask planning because, as Sergey has mentioned, right, different robots have different state and action spaces. But now essentially we're turning planning into a unified interface, unified task, which is just to condition on language and some initial frame to try to generate the video. And we can do this for any robots because the pixel space is actually the unit shared observation and action space across different embodiments of different robots. And there's one other usage of Unisim, which is we can generate training data for VLMs because one of the bottleneck for VLMs perhaps like the amount of labels that we have for this paired image and text. So in this case, we can actually generate videos for cutting pepper using Unisim. But then we can take these, because we condition on cutting pepper to generate this video, and that if the video generation model is good, then the videos that we get is in fact the video of cutting pepper. So we can use that paired video text pair to train a video captioning model. And the observation is that we can actually improve the transfer performance of these video captioning models when we train it on simulated data from Unisim. Okay, so that's the second part of today's talk, which is the takeaway is really once we've learned this real-world simulator, we can actually apply a diverse set of decision-making algorithms such as reinforcement learning and planning in the simulator to optimize policies. And okay, next I want to talk about some challenges and next steps in terms of how to address them. So one challenge, this video is actually from Sora, which actually was kind of developed 6 months after Unisim. It's something that's hard to argue because it's just so much more popular. But yeah, I just wanted to say like we kind of worked on this a bit earlier. And so in this example, you saw like the chair was just jumping around without people touching it, right? So this is really like violation of real world physics. And in fact, not Sora has that, Unisim has that as well. If you look closely, you see that the carrot actually grows into the knife as opposed to the person cutting the knife, right? So you might be fooled by these videos, but it's really not okay to use these videos to control robots when they hallucinate a lot. So we so far don't have really good solutions to hallucination. Scaling helps a bit, more data helps a bit, but I just wanted to like give a more optimistic point of view, which is at some point, hallucination could also, depending on the definition of hallucination, but we also wanted a bit of an imagination in situations where we have unrealistic language instructions, right? So in this case, we have a tabletop robot with a robot arm, but the language instruction says wash hands. Right? So this is clearly unrealistic because there is no hands in this image. And I was really surprised to see what happened in Unisim, which is like the video that got generated, was just that the view shifted from this tabletop into a kitchen and a person's hand shows up, right? So this is really showing something that the model is trying really hard to generalize to this novel language input by using the training data to do what's most probable, what's most likely, which is to just turn away from this view. So I think in some sense hallucination, yes, it's bad, but in some other cases, like there are these interesting observations. And the next question is, okay, we generate a video, but how can we know if it's good or not, right? So we can have humans look at it, but it's not very efficient. So in some sense, I actually think robotics or embodiment is actually a nice way to automatically verify the quality of generated videos. What do I mean by that is that imagine like we had this diagram from before where we had these search trajectories or generated videos, and now we turn these videos into actions and execute these actions in the real world. Then the question is, should good world models lead to successful robot executions? And then the answer is yes, right? So essentially we're trying to match these two parallel universes. One is the real world and one is the imagined this world model that the agent uses to imagine into the future. And eventually, if the world model is perfect, then the actions extracted from the world model should also execute in the real world and results in the same video as the one that the robot has imagined. And when there's something goes wrong, right? Like for example, the real world video that the robot gets actually doesn't match what the robot has imagined. This is like a realization for the agent to further optimize its video generation model or its policy based on this real world feedback, because clearly we run the robot and we see the robot crash or something. So this is like additional thoughts on in terms of how we can evaluate video generations using robots and how to incorporate feedback from the real world, in addition to just human feedback. And thank you. I wanted to thank all of my collaborators from Google, Berkeley, and MIT. And I guess it's time for questions.
Any questions on the phone? Okay, yeah, I got one question. So it's a general thought on how to apply the foundation models into the robotics. So one paradigm is to apply what we have in VLMs or LMs and then fine-tune into the different kind of the robotic pathway. And another one is to utilize all the data pyramid of what we have in the robotics and create the robotic foundation model itself. So what kind of paradigm do you prefer or you prefer?
Yeah, I think the answer to that question really depends on like the task itself and the data available. If you talk to some classic roboticists, they don't even think learning is needed, right? So, but then like all they can do is that particular task, like maybe just a screwdriver screwing this one screw, and once the shape of the screw changes, they can't do anything about it. So, but then like what internet scale knowledge brings you is this generalization, right? Like the bartender example, which is something that's really only the internet scale data sets have these kind of knowledge. And if our goal eventually is complete automation without expert knowledge, going from language to robot actions, then we really need these visual understanding and linguistic understanding of the tasks. So this is when like these internet scale data sets become quite relevant. Like if you're saying like we already broke down the task, we already figured out like the details, like these classical robotics, then the question is like how do they generalize? So I think this is where internet data helps. Yeah.
I'm really interested in now about the evaluation. I understand correctly what you mentioned to do some closed-loop evaluation. But imagine we are doing very large-scale video generation simulation. Is that expensive? Do we have any way to evaluation?
Yeah, so there are definitely these proxy metrics that you can use from generative modeling, like such as FVD, like which is the FID version of for videos. There are also these like clip scores. You can look at how the generative video, whether they're following instructions. My experience has been that these metrics are reliable to a certain degree, but sometimes like it's also not because it's distributional like information. So it's yeah, like I could still get like hallucinations and so on. So I'm just proposing, I'm not saying like all videos should be verified using robots, because you might have videos that are just humans, or you don't have robots that you can't really turn that video into real world executions. But I'm just offering robots as kind of like a convenient way to verify video generation. So we do have generative videos of robots to test whether this actual generation corresponds to good robot execution.
Thank you very much. I'm from remote, so we fly the car on the road.
Yeah, I guess another evaluation is like you can roll out your policy in a simulator and see how it performs. That's yeah.
What are some of your insights on the breakdown? Horizon.
Yeah, so this is actually going back to like how we process the data, and it actually depends on like the task consumption. Like we have a fixed number of frames during training. We fix that number of frames, but then depending on the frame rate at which we sample, different data sets have different frame rates. But essentially what we need to do is kind of align the duration of the video and the language instruction, like roughly. And that actually gives us a lot of flexibility of incorporating data sets recorded at different frame rates and so on, as long as we can like actually have like a fixed window to capture what happened in the language instruction.
You observe any synergies between training on different tasks and domains, or the network basically encodes like different tasks?
The question is, do I observe whether the network encodes different tasks into subspaces? So I think the answer is yes. And to actually be very honest, like I think the current video generation model conditioned on the first frame doesn't work super well out of domain. Like when you give it like some really absurd image taken from really absurd angle, for example, and I try to interact with images and it doesn't really work well. And usually if I get an image from the internet distribution, it seems like the interaction works well. So which means that you know, like the model is doing kind of something about these visual observations, and once we actually go beyond the distribution of these visual observations, we're actually in some trouble. And I think how to like mitigate or improve out of domain, by domain I mean image observation, generalization, I think is a very interesting direction to be worked on for this image conditioned video generation models.
Let me ask it in a different way. So you have this like log pushing task and like the Google robot opening drawers. If you train on both of the tasks, you get better performance, or is it like?
Yeah, we have some ablations in the paper that yes, we do have better performance metrics according to the simulated metrics. We actually didn't run real robot experiments to verify that, because there are many things involved, inverse dynamics and so on. But according to the simulated metrics, including more data, does improve generalization on the test.
Yeah, please go ahead.
Thanks for talking. In regard to the hallucination, I'm wondering if you observe on longer time scales, more complex hallucinations. Because I look at the direction of the camera, like when you turn into the dining room, you're now in a complete generative space that's completely different from your initial state. So if these are long range tasks, do they affect the output, and you get a video issue going forward?
Yeah, so I guess the long horizon that I showed you did have a fixed camera angle, and it's only doing manipulation. And my hypothesis, we haven't really run that experiments, but I guess one challenge for the model is to have long-term memory. So for the example that you gave, if the model didn't really encode, like for example, we only use 4 frames from the past to condition on to generate a new video, so which means that the model isn't able to turn to the dining room and turn back to still see a kitchen if the kitchen wasn't in its memory. So in that case, hallucination definitely happens. So these are more egocentric issues. There's also the issue if your language instruction is too abstract, something like, yeah, like if you don't break down the task into the distribution of language that was in the training data, if it's too abstract, then it's also hard for the model to generalize. So essentially, it's like the distribution of training data, whether like the language is actually in distribution. Yeah. Yeah, I mean, that's the whole tree search, which is like we can at inference time utilize language models and to kind of break down the task so that it's more in distribution. And I think like the text to video data set will probably get bigger and people will have very diverse labels. Like it will be something very specific, you know, something moves by 2 centimeters, or something very abstract, like a person cooking. So, and we can, because the model is so flexible in that it can condition on very diverse actions or very diverse language to generate the frames that corresponds to those executions, we can actually merge all of those data sets of different granularities. Yeah.
Data generation as the ground truth, like as the like your language, right? So if the language does something stupid, then the data does something stupid. So something similar to enforce consistency in videos, like let's say the road, right? On the road, in the lab, I do have a ground truth simulator like we're supposed to roll. We can use something that can keep the videos, I know that.
Yes, I think so. And in fact, we already have something like that. So, you know, we're generating videos and then we're using another vision language model as like a critic, like a reward model to tell which video generation was good, right? And so my understanding is that these text to video models and these vision language models are trained on perhaps slightly different data distributions. And as a result, they have slightly different knowledge about the world. And by just having these 2 models communicating with each other and correct each other and providing additional data and so on, we can actually get a bit of additive effect of performance. So in fact, yes, we do already do that. Yeah.
Sure, go ahead. We might have one last question.
So I personally feel like gaming and information has been so I'm gaming data is by that field. So have you ever think about try to inject that field gaming data?
Yeah, not for Unison, we do have a follow-up work called Video as the New Language for Real-World Decision Making. And in that case, we actually included game data. And my sense is that because there is a lot of game data and oftentimes they don't have very good language annotations, some of them are just like, you know, players talking to each other. It's not really capturing like what happened in the video itself. So we didn't like observe a drastic gain by including video data sets. But I think the fact that if we can just scale up the model infinitely and we can absorb more and more data, because the video data does also have this notion of keystrokes and response to keystrokes, which is pretty much like what robotics are. So controls and next alterations. So yes, I think ultimately including video data that would be helpful.